synthesis and then how it is eventually excreted or excreted as a bile. So, why is this important to understand? Well, bilirubin is a yellow pigment that is formed because of the breakdown of heme. And so, the breakdown of heme is primarily due to the senescence of the red blood cells. So, red blood cells broken down leads to the breakdown of heme. And then once bilirubin is formed, it will be processed by the liver before being excreted into the bile. So let's talk about the step-by-step breakdown of, or let's have a step-by-step breakdown of how bilirubin synthesis works. So number one, you start with the breakdown of heme. The breakdown will be done by the macrophages in the reticuloendothelial system. And so this will mainly occur in the spleen, the liver, or even the bone marrow. Well, anyways, the heme comes from the hemoglobin in the red blood cells, and once that is broken down, it leads to the production of biliverdin. So, as shown right here, we have the red blood cell giving or contributing to the hemoglobin. We break down the hemoglobin into the heme and the globin, and the heme will be broken down into the biliverdin through the enzyme called heme oxygenase. So the heme oxygenase helps break down heme, and you get the biliverdin. The byproducts you get is the iron that is recycled, and then actually it's a carbon dioxide. Yeah, my mistake there. Glad that we got it. So byproducts can be iron or in the ferrous state that is end up being recycled. So then it can be used to have more red blood cells, and carbon dioxide will obviously be exhaled. Then once we have the biliverdin, then we need to get our bilirubin. And the way we get our bilirubin in the unconjugated form specifically is through the enzyme called the biliverdin reductase. So the biliverdin reductase will be occurring this step. It utilizes an NADPH molecule to basically help produce bilirubin from the biliverdin, and as a result you produce an NADP plus molecule. So once the biliverdin reductase helps convert the biliverdin into your bilirubin, the bilirubin in this state is unconjugated. And the way you know it is unconjugated is that it is water insoluble. Now we are still in the blood, and basically we need to get to the liver. So how do we do that? It must be bound to the albumin. Okay? And remember that the unconjugated bilirubin is lipid soluble and not yet water soluble. So remember that must be bound to the albumin specifically. And the unconjugated bilirubin, once it is bound to the albumin in the blood plasma, it will be carried to the liver for conjugation. So unconjugated bilirubin, it travels all the way to the liver, and this is where we can finally conjugate the bilirubin. So the conjugation of the bilirubin will happen in hepatocytes, or the cells in the liver. this process will be facilitated by the enzyme called UDP glucuronosyltransferase, or UGT1A1, as shown over here. So the UDP glucuronosyltransferase will facilitate the conjugation of bilirubin. And so as a result, the conjugated bilirubin is produced in the liver. In other words, bilirubin becomes conjugated with the more polar glucuronic acid, and thus it becomes water soluble. And so this is a good point to talk about some clinical correlates. So impaired conjugation can lead to unconjugated hyperbilirubinemia, where the bilirubin cannot be conjugated at this phase, so it remains unconjugated and it starts pooling up in the plasma of the blood. And this can lead to the condition called unconjugated hyperbilirubinemia, and it can have detrimental effects, especially to the brain. It can definitely have the patient present with jaundice, as is this classic Gilbert syndrome or Crigler-Najjar syndrome. I don't know if I pronounced that correctly, but you can let me know in the comment section. Anyways, once we have produced a conjugated bilirubin, now it is time to excrete it through what we call the bile. And so at this point, the conjugated bilirubin will be actively transported into the bile canaliculi, specifically through the transporter called the MRP2. MRP2 stands for the multi-drug resistance associated protein 2. And through this transporter, the bilirubin that is conjugated will flow in bile into the intestinal lumen. So once we get to the intestine, specifically in the terminal ileum and the colon, the bacteria present there will actually deconjugate the bilirubin and convert it to urobilinogen, as shown over here. So this is the step we're at. And the urobilinogen is interesting because some of it will be reabsorbed into the portal circulation, or the veins traveling back to the liver. This is known as the enterohepatic recycling. So reabsorption of urobilinogen through the portal vein back to the liver. Remember, that is enterohepatic recycling. Now, other urobilinogen will be transported to the kidneys, and from there they will be excreted as urobilin, and thus they will contribute to the yellowish color of the urine, as I wrote down over here and as shown over here. On the other hand, most of the urobilinogen will actually be oxidized into a stercobilin. And the stercobilin is what gives your feces or your poop its brown color. So the next time you poop and your poop doesn't appear brown, well, you can go ahead and assume that something compromised this step that would normally allow for the urobilinogen to be converted to be oxidized to stercobilin. Or it can be due to something that happens before that. Maybe there's not enough bacteria to deconjugate the bilirubin, leading to decreased urobilinogen amount. Or it could be something that relates to an obstruction with the bile duct itself. Who knows? It could be any of that. And so that's why we have this clinical note here where when conjugated bilirubin cannot reach the intestine, we have obstruction that prevents conjugated bilirubin from reaching the intestinal lumen. So, in summary, what basically happens in bilirubin metabolism is that the red blood cell is broken down, you get heme, the heme gets broken down, and you get biliverdin through an enzyme called the heme oxygenase. Biliverdin converted into conjugated bilirubin through your biliverdin reductase. Then the unconjugated bilirubin binds the albumin and travels to the liver, and there in the liver, the bilirubin is conjugated through the UGT1A1 or UDP glucuronosal transferase. After that, the conjugated bilirubin travels to the intestine as a bile or as part of the bile, and once in the intestine, it is converted to the urobilinogen. And that is facilitated through bacterial deconjugation. And then once it is converted into urobilinogen, it can either be excreted as a stercobilin through the feces or the urobilin through your urine. So that's all for today regarding bilirubin metabolism. Let me know if you have any questions about this topic, or feel free to comment down below any clarifications that need to be made or any corrections that need to be pointed out, because I am not a perfect lecturer, and sometimes, or most of the time, I make mistakes. So yeah, just verify that all this information is correct. In the meantime, I hope you enjoyed this video, this ASMR